So the title of my presentation is going to be Hyperbolic Distance Geometry Problems. This is a joint work with Professor Dukmanich. And hopefully this would be a summary of our work in the past 2 years. I will start with the motivation behind considering hyperbolic spaces and trying to solve distance geometry problems there. Then I will get to the outline of the talk later on. Okay, so in the most kind of basic sense, distance geometry problems aim to realize a set of points in a metric space, usually Euclidean space, given a set of distance-related measurements. And I use the word distance-related because not always we have exact distances or distances. In some applications, actually many applications, we have dissimilarity data that are different from distance measurements, and I will get to them later on. But from here on, I keep talking about dissimilarities. You can, in your mind, replace it with distances. Okay, so here's an example of a DGP. For a set of 5 entities in an application, you can have a set of dissimilarity or similarity measurements between these pairs of points, and you might have some missing measurements here as well. And the goal is to find a realization, for instance, in R2 that best represents this measurements. So if the dissimilarities are, for instance, Euclidean distances, then you can think of multidimensional scaling, PCA, and other variants of metric DGPs as solvers, or as variants of DGP solvers. Another line of work that kind of related to distance geometry problems are manifold learning problems, where we have the distances between pairs of points, but we only focus on local distances, or the distances within some neighborhood of an entity. And we would like to find an embedding, a low-dimensional embedding that captures this local geometry of data points. So in a sense, even manifold learning problems could be an instance of distance geometry problems. So we've already covered many applications of Euclidean DGP, so I just rehash them again. One application could be molecular conformation, where we have nuclear magnetic resonance data, and we transform them into distances between atoms, and we try to solve DGP. We try to solve find the molecular structure that realizes this data. This is an instance of unassigned distance geometry problems, where we don't know basically which pairs these distances are related to, pairs of points. Another application would be sensor network localization, where we have signals, their strengths or their time of arrival, and we transform them into distances between nodes. And the goal is to estimate the topology of the network. Or other application could be robotics, where we have robot swarms, lots of robots, and these robots get to communicate with each other, being neighboring robots, and share distance information, but we don't have the global distance information, and we want to localize all of these robots at the same time. So these are real world applications of DGPs, where the data points belong into R2 or R3, but that's not the end of the story. We might have other types of data that usually are associated with graphs. And especially here, we are talking about trees. And you can think about it as having an underlying tree, which you may not even know what that tree is, but you have reasons to believe that there is a tree, and you get to see similarity or dissimilarity scores between a set of entities or nodes on that tree. And these dissimilarities are generated via a function of distances on the tree that are defined on the tree. So here, if you have similarity scores like this, then it's not obvious that Euclidean representation for this tree could be optimal. As a matter of fact, I will show that it wouldn't be, and we have to go about embedding such dissimilarity measurements in hyperbolic spaces. And such data can be found in many domains. For instance, you can think about taxonomies in biology, where we have different species, and we know that there is an underlying tree that explains the different categories of these species. And so if you want to find a representation and visualize this taxonomy, then we're talking about embedding a tree. Or another application would be concept hierarchies in computational linguistics, where we have, for instance, words that they have semantic hierarchies between each other. And if you want to embed these words and find a vector representation for these words, then we want to leverage these hierarchies so that we get a better, more meaningful embedding for them, and subsequently perform different tasks, natural language processing tasks more efficiently. So why are we considering hyperbolic spaces? Well, in 2011, Sarkar showed that hyperbolic spaces can embed hierarchical structures or more specifically weighted trees with arbitrary low distortion. And this was in just two-dimensional hyperbolic space. And the distortion was up to a multiplicative scalar, but for most applications, that doesn't really matter for us. And and one kind of simple way of thinking about it is that you can think about a tree that is growing, whose depth is growing. So the number of leaves, if you have constant branching factor, would grow exponentially. And if we want to embed this tree in Euclidean space, we better be able to have enough space basically to embed this tree. And a simple reasoning basically says we don't have enough space because the radius of a ball in Euclidean space grows polynomially, not exponentially, in Euclidean space with dimension, with radius. So, but in hyperbolic space, this volume grows exponentially, even for two-dimensional. So in a sense, hyperbolic space is a little bit more roomier to embed tree-like structures. And here I did a real simple experiment. I generated one specific tree, weighted tree, and I embed them in B in Euclidean space and in A in hyperbolic space. So the goal of the embedding is to represent these pairwise distances that are defined on the tree. And then I went about doing like k-means clustering on both of these. And these are the clusters I get. Here, this is a point radius. This is a hyperbolic space. I will get to talk about it later. But visually, we will have more meaningful clusters in hyperbolic space. And this is due to the fact that our embedding was more faithful, represented those pairwise distances on a tree better. So because we have better embedding, then we can have clusters that are meaningful, and that is actually what we want to do. Um, so there are other examples of hierarchical data. For instance, I talked about word embedding applications. Uh, you can also have phylogenetic tree where you have, let's say, a set of microorganisms, and you know that in this sample of like, I don't know, a million microorganisms, there is going to be a tree that explains the evolutionary history of these microorganisms. And here's a like one specific tree. This is not an embedding. This is just a visualization of the tree. And if you want to embed this tree and do like subsequent like task like placing a new node on the tree or placing a new microorganism in the tree. So then you need vector representation and embedding. So we're arguing that if you do that in hyperbolic space, you will get better results because you can have a better embedding. Another application could be, again, in biology, where this is a Nature Com paper in 2020 when they reasoned that cell developmental processes can be thought as moving trajectories along trees, basically immature cells getting branched out and develop into more mature and specialized cells. And this can be represented via a tree. And so they defined similarities between these cells, and they went about embedding these similarities in hyperbolic space. And the goal is to do a whole lot of tasks such as like visualization, lineage detection, pseudo-time inference, and so on and so forth. And so this is an example of that embedding, and they argue that doing these in hyperbolic space would give you a better performance compared to the Euclidean space. And by the way, this is just two-dimensional hyperbolic space. Okay, so for all these reasons, I'm considering solving a distance geometry problem in hyperbolic space. So here's the outline of the talk. I'm gonna talk about what are hyperbolic spaces and what is a distance geometry problem. And then I will talk about Procrustes analysis in hyperbolic space, which is, quite common if you're trying to solve a DGP in Euclidean space. You want to be able to align point sets. And then finally, I will end the talk by asking a kind of a fundamental question and kind of abandoning this, tree-like structure, talking about just similarities in general, and if they entail any geometrical information, or if you can derive some geometrical information from similarities or not. And the answer is yes. Okay, so hyperbolic spaces. There are 5 different models of hyperbolic space, and here are all of them. Half space, Poincare, hemisphere, Klein, and Loid. And in most machine learning papers that utilized hyperbolic spaces in their work, they consider Loid and Poincare model, just because it's Poincare model is this disk right here, and it can be used to visualize like hyperbolic point sets, which I just did like 2 seconds ago. But Loid model, which is this hyperboloid, is in my opinion is pretty good for optimization purposes. But as far as distance geometry is concerned, all of these models are equivalent because there is a distance preserving bijection between all of these spaces. So if you can embed your point sets in one of them, you can just transfer them to some other space and visualize it there. Okay, so this is a Loid model. And we want to know what is the shortest path between 2 points in the Loid model. And like geometrically, it's quite easy. You can have X and Y, and you take the span of X and Y, which is a 2D subspace, and then you take that intersection with the hyperboloid sheet, and then this line would be the shortest path line, aka geodesic. And you can use this bijection that I just mentioned, stereographic projection, to basically visualize this geodesic in Poincare model as well. So as you can see, the lines don't look straight, but they are shortest path lines between these points. And the closer these points are to the boundary, the more curved they're gonna look. Okay, so before formalizing what Loid model is, we have to know one very important and simple definition, and that is Lorentzian inner product. Lorentzian inner product between two vectors in Rd plus 1 is defined like this: X transpose Hy, and H is an indefinite matrix. So it's a diagonal matrix. Its first element is -1. All the other elements are 1. And so this is an indefinite inner product, but from here on, I'm just going to call it inner product because it's going to show up quite a bit of time. It is indefinite because if you take X and multiply it by X, it can be negative, right? Because H is indefinite. So with this inner product, a special inner product, you can define like familiar notions like adjoint or unitary operators. But we're going to put an H before each one of them to make sure that we know what we're talking about. Okay, so this is the definition of Lorentzian inner product. Now we get to the definition of just the Loid model. Loid model is a d-dimensional manifold. Its domain is a subset of Rd plus 1. But those points whose inner product with themselves is -1, again, this is a Lorentzian inner product. And the first element must be positive. So the domain is fully characterized by this Lorentzian inner product. And the Riemannian metric there is constant for any base point that you choose. And again, is defined by the inner product between these tangent spaces, tangent vectors. So basically, Riemannian metric, for anybody who is not familiar, is a generalization of inner product for manifolds. Okay, so the manifold is fully characterized by this Lorentzian inner product. Also, the distances, the closed form distances between any 2 points on the Loid model is also characterized by this Lorentzian inner product. This is the formula: a inverse hyperbolic cosine of minus inner product of X and Y will give you the distance between X and Y. So it seems very crucial that we should really get to know Lorentzian inner product before trying to solve anything in hyperbolic spaces. Okay, I talked about tangent spaces, but so this is kind of a tangential slide. So I'm gonna just tell you like what it is. The tangent space at point X of the Loid model is basically all the points whose inner product with X is 0. Again, this is characterized by Lorentzian inner product. And so I don't do that, but if anybody want to do kind of implement a learning method that is gradient based, so then you need to know how to move on this manifold, and the way you move is you move in the tangent space and then you project back to the Loid model, and then this projection is called exponential map. where you get to project a vector in the tangent space at X to the Loid model. And this is the expression for it. And all of these norms and everything, again, is with respect to that Lorentzian inner product. So Loid model, in a nutshell, is fully characterized by Lorentzian inner products. Okay, so now that we identify what Loid model is, let's formalize what distance geometry problems are. Okay, so this slide is basically is the pipeline of solving any distance geometry problems in hyperbolic spaces. With if we are trying to solve it with semi-definite relaxation. So okay, let me explain what hyperbolic DGPs are. We want to find an embedding for a set of entities that realizes a given set of distances or similarity measurements, and similarity measurements. So distances are what I call metric measurements, and similarities are what I call non-metric measurements. So I kind of represent these kind of measurements in this box. Metric measurements is where we know the distances between pairs of points, and non-metric measurements, as I will show, can be interpreted as distance comparisons. Like when we say 2 points are more similar than 2 other points, then that means the first 2 points should be closer than the other 2 points. So similarities are distance comparisons. So that's why we have these inequality constraints here between different types of pairwise distances, different pairwise distances. So we have these measurements, and I'm going to encode them or tabulate them in a matrix, n by n matrix, that basically represent all of the pairwise distances between these entities. So this is a distance matrix. So as you can see, we might not have all of the distances, but we might have some of them, and they can be noisy. And I will show that with a semi-definite relaxation, we can denoise this matrix and estimate the missing measurements. And once we have all of the pairwise distances, then we can do a simple spectral factorization of this matrix to estimate the point positions here in like hyperbolic space. Okay. So this is the whole pipeline. So I'm gonna talk about distance matrices and what semi-definite relaxation means, or semi-definite characterization of these distance matrices are. And then I'm gonna finish with the spectral factorization. So, okay, so a hyperbolic distance matrix encodes all the pairwise distances for a set of points in the Loid model. Okay, so distance between x and I and xj, as we mentioned, is inverse hyperbolic cosine of their minus inner product. And the inner product is defined like this, right? So this is a Lorentzian inner product. And HDM is basically a collection of all of these pairwise distances, which we are gonna put it in the matrix D, and we put the collection of all these pairwise distances in a matrix called G, which is hyperbolic Gramian because it encodes all the pairwise inner products. And it is hyperbolic because the points are hyperbolic. And this G can be written as X transpose HX. So again, we have this H in the middle. So this G matrix is not a semi-definite variable, and we want to solve this problem with semi-definite relaxation. So by lifting the parameters from X domain to G domain and finding a semi-definite characterization for this G, we're hoping that we get to the place that we want. So in the next slide, I'm going to talk about how to represent this G in terms of positive semi-definite variables. Okay, so this proposition basically formalizes our claim. Let G be a hyperbolic Gramian for a set of points, endpoints. So then we can write G in terms of subtraction of two positive semi-definite matrices. Okay, so G is not a semi-definite matrix, right? And there is going to be this rank constraint for G plus and G minus. And this is to ensure that this G here encodes all the Lorentzian inner products, this rank constraint. And all the diagonal elements of G must be equal to -1. And this is to ensure that inner product of every point with itself should be -1 by definition. And then all the off-diagonal elements should be less than -1. And this is a technical thing to ensure basically all the points belong to one sheet of hyperboloid, because you can have two sheets of hyperboloid. Anyway, so this is a semi-definite characterization of hyperbolic Gramian. Okay. And by the way, we have the converse as well. So any matrix that satisfies these constraints is a hyperbolic Gramian. So a proper hyperbolic Gramian for a set of endpoints in D-dimensional space. Okay, so now we want to solve DGP in hyperbolic space. So for metric measurements where we have the like noisy pairwise distances, we want this condition to hold. We want Dij, which is the noisy measured distance, to be approximately what we get after embedding the points, right? But this is a nonlinear function of our parameter Gij. So what I'm gonna do, I'm gonna take hyperbolic cosine from each side, and I'm gonna say, okay, we want hyperbolic cosine of our measurements to best represent this parameter. And if I do that for all ij's that I have the measurements for, metric measurements, then I can have something like this. Hyperbolic cosine of all of the measured distances should best represent minus g, so plus g here. And I will measure it at the indices that I have the measurement for, right? And I want this error to be less than epsilon. That's data fidelity constraint that I'm gonna have for my semi-definite program. And as I mentioned, non-metric measurements are basically distance comparisons. So we have these constraints. We want some distances to be less than some other distances, based on the similarities that we measure. So if we follow the definition, we have this, and because inverse hyperbolic cosine is monotonic function, then we would have they will have this constraint as a linear inequality constraint on G, basically. So the bottom line is linear and quadratic data fidelity constraint can impose a good embedding like constraint for metric and non-metric data. So this is our proposed semi-definite relaxation to solving this problem. So we want to minimize the rank of those two matrices. So instead we say, okay, we can't do that. So let's minimize the trace as a surrogate of these matrices. With respect to them being positive semi-definite, their difference should be hyperbolic Gramian. It has to satisfy the hyperbolic Gramian conditions. And also during the embedding, it also has to satisfy some data fidelity constraint. It has to respect the measurements. This is a metric measurement and this is non-metric measurements, right? So this is a linear inequality constraint and this is quadratic constraint. And these are linear. So this problem, can be solved with like relatively easy with like available SDR packages. Okay, so after you solve these for G plus and G minus and you come up with your hyperbolic Gramian, almost surely the rank of this matrix is not going to be correct because we relaxed the rank constraint. So we have to do some sort of projection and subsequent Riemannian gradient descent to correct the rank. So I'm not going to get into detail of that, but let's assume that we've done that. And now we have a hyperbolic Gramian of the correct rank. How do we go about estimating these point positions at the end? So it's really easy. A simple eigenvalue decomposition on the G would give you eigenvalues that are positive and negative. So you take absolute value of that, the square root of them, multiply by the eigenvectors, and you have your point sets. But here R is not your average, unitary matrix that you have for hyperbolic for Euclidean spaces. This is, as you guessed, this is an H unitary matrix because of the Lorentzian inner product business that we talked about. So there's this ambiguity. We don't know the exact location of X, but we know it up to an isometry. Okay, so here we conduct an experiment. It's very simple. We generate random hyperbolic point sets, and we measure their distances, and we just deselect some of them, sparsify them. And now we have a distance matrix with missing measurements, and we run our semidefinite relaxation to estimate the missing measurements, and we're going to report the maximum sparsity level that this semidefinite relaxation can take while giving us a good reconstruction. And this basically shows the maximum sparsity level grows with the number of points that you generate. And so this is kind of similar to Euclidean spaces as well. So the more points you have, the sparser your distance measurements can be. And we'll repeat the experiment with non-metric measurements. Again, we generate random points. We can compute their distances, but we totally ignore distances, and we just retain distance relationships like inequalities. And we subsample those inequalities or non-metric measurements, and we embed those basically inequality measurements or non-metric measurements. And here's the relative error, embedding error that we get as a function of like the number of points. It goes down. Also, we get to have, this is a sparsity level, we get to have a sparser and a sparser measurements for the more we have, the more number of points we have, right? So it does a good job for metric and non-metric measurements for just purely hyperbolic point sets. So we're going to repeat the experiment with like weighted trees. Now we generate random weighted trees with random weights, and we embed them in hyperbolic and Euclidean spaces. But this time we're gonna change the embedding dimension, and we're gonna find the best, or like the minimum embedding dimension that the embedded points are they satisfy a certain accuracy level. Like their pairwise distances should accurately represent those that are from the tree. And so for each realization, for each random tree, we have a specific optimal embedding dimension for hyperbolic and Euclidean. And here you see the y-axis is embedding dimension, and this is basically the distribution of embedding dimension. Red is for hyperbolic point sets, for hyperbolic embedding, green is for Euclidean embedding, and this x-axis should be the number of points in the tree. So the optimal embedding dimension for Euclidean spaces is growing faster than hyperbolic spaces. And that, again, stands for the fact that if you're dealing with weighted trees or any tree like a structure, you're better off embedding them in hyperbolic spaces, at least in dimension, and, and, and in some ways in accuracy as well. Okay. Okay, so this was solving hyperbolic distance geometry problems. Now, as many of you are aware, in solving DGPs, usually you have ambiguity in the exact location of the point sets. You need some anchors to find them. So, and that's the problem. That's what Procrustes analysis is trying to solve, right? So here we say, how can we ask the exact same question? Well, we have like kind of this tree language. How can we align two embedded trees that have few nodes in common? Like now aligning means like finding an isometry or distance preserving map that best basically superimpose these two structures together. So the answer is Procrustes analysis, and we just had a paper that was accepted in signal processing letters on it. And the idea is to find an isometry between two sets in hyperbolic space that best superimpose them together. And here's like a cute visualization for it. So we have the far right and far left point sets, and we know that they are related through an isometry, the distance preserving map. How do we go about estimating this map? Well, it's really easy. It's quite similar to the Euclidean spaces, in which we basically center each point set, and we find the unknown rotation that basically finishes the job. And this is exactly the case for hyperbolic spaces as well. And I'm going to talk about like basically isometries in hyperbolic spaces, and translation, rotation, and how do we go about centering point sets in hyperbolic space. So so our analysis is based on the fact that any isometry, hyperbolic isometry, can be decomposed into two elementary maps: translation and rotation. And they are given as follows. So if T is an isometry, it can be written as the product of two matrices, basically. RU is the rotation. We can think about it as operator. And RB is quote unquote translation. And it's characterized by d-dimensional vector B here. And that B basically shows the direction that we want to translate these point sets. And we call them translation and rotation, but especially translation, that it doesn't behave like Euclidean translation. Like it doesn't move all the points with the exact same Euclidean distances. But it does have the property that we want it to have, which is RB inverse is R minus B, which is kind of like the property that you would want to expect from a translation, at least. So here I visualize these two operators. So we have 4 point sets here, and I'm gonna apply consecutive rotations on these 4 points, and I'm gonna rotate them. And this is the locus of the points that we get in Euclidean, in Poincare space, and this is just a perfect circle. So just the simple rotation means hyperbolic rotation, right? But for translation is a little bit different, and this is the direction of the translation that I'm gonna define. So I'm translating all these 4 points in this direction, and each time a little bit more than previous time. And this is like basically the locus of all of these vertices. And as you see, they're kind of look like they're converging to one single point. And that's okay, because the distances here near the boundary of Poincare basically blow up. They may look like they're converging, to a single point, but actually all of these pairwise distances remain intact. So so this is how translation works in hyperbolic space. Okay, so there are two problems when it comes to solving Procrustes analysis. One is the notion of center mass in hyperbolic space. Usually in Euclidean space, center mass is the point that kind of minimizes some sort of discrepancy or variance. But here we define it kind of differently. Actually, this is not my definition. You know, you can find it in the literature as the point to be maximizing some average inner product, basically. This QZ is the center mass, and it maximizes some average inner product. And once we find this QZ, we map it to Z, which is in this plane. And that will be our center mass, basically. And we have the following lemma, basically, or proposition. If we have two point sets that are related through an isometry, which is a rotation and translation, after you center each point set, then they're only related through a rotation. So by centering, we simplify the problem and we get to just basically estimate the unknown rotation. And the unknown rotation, again, is really simple. We just want to maximize this average inner product, basically, between centered point sets. And this can be done by singular value decomposition, very similar to orthogonal Procrustes problem of this matrix, basically, like centered point sets product, basically. So this is the gist of hyperbolic Procrustes. And now for the final point of my talk, and that's kind of like a fundamental problem of figuring out or trying to reveal the underlying geometry of similarities. So, you know, most often than not, in practice, truly hyperbolic distance measurements are rare, unless we know that we're dealing with trees or yeah, or like we have some strong like assumptions, or we just want to solve the problem in hyperbolic geometry. But most often we have only similarity measure. We don't even have distance measurements. We only have similarity measurements. And you know, there are so many examples of similarity measurements. You can think about correlations and co-occurrences. You can think about perceptual crowdsourced data. You can think about like lots of biological data where you get to measure the activity of neurons, for instance, and compare them together. So there are so many like similarity measurements. And the question that we're asking is, can we reveal the geometry of like underlying geometry of these similarity measurements? And we're not going to use any metric information. We don't know the pairwise distances between these entities. So this is kind of a general question, and we have quite a bit of like theory about it, but I just want to convey the basic ideas that we are thinking about this problem. So similarity measurements, we have this kind of, depend on who you ask, kind of simple or very strong assumption. And that is like similarity measurements Yij between 2 points I and j is just a non-linear function of the distance between xi and xj, the embedded points. And this phi is monotonically decreasing. So if they are closer, they are more similar. If they are farther away, they are less similar. Okay. So like an example would be you have a data graph and you get some measurements here, and you know these are similarity measurements. So what this assumption basically says is that there is a metric space in which these x's reside in, and there is a distance function on it. And there is, again, a phi, unknown phi function, such that these phi of these distances basically realize these similarity measurements, right? So this is the basic assumption here. And because we're assuming that this phi is monotonically decreasing function, and we don't know what that is, the only way to interpret these similarities is that just to change them into ordinal or non-metric measurements. And that is like this. If what I said, like if I and j are more similar than k and l, then xi and xj should be closer to each other than xk and xl. So these similarities are just as informative as these distance comparisons, just because phi is, unknown and decreasing. Okay, so here's an example. Let's say we have similarity scores between 6 entities. And so we know how to like transform these similarities into distance comparisons. So at the end of the day, I can get a sorted distance list by just sorting these similarities, right? And so I basically summarize these similarity measurements into a sorted distance list like this. And I don't know what the underlying geometry is, and I don't know what the distances are, basically. I just know these indices and the pattern of these indices. And the idea is to extract some features from these indices that are indicative of the underlying geometry, hopefully, of these x's. So our proposal is a notion called ordinal spread, or alpha k. And that is, alpha k basically is the ranking of the first appearance of the kth point in the sorted distance list. So I'm going to go through different k's, and I'm going to basically illustrate what it means. So alpha 1 is the ranking of the first appearance of the first point. So first point is x1, and its rank here is number 1 because it's the largest distance. So alpha 1 is 1. And the second point appears for the first time here again. So its rank is also 1, so 1. And the third point is x3 appears in the second rank. So there we go, 2. These 2 points have already appeared, so I'm going to skip that. x4 is the fourth point that appears at rank 4. x5 is the fifth point and appears at rank 4. And x6 basically appears, let's say, at 11th rank here. So I just derived the vector from these patterns, basically. And this is the ordinal spread vector, let's say, okay? And there is some evidence to be had that basically the last index is quite important. Basically, the ranking of the last point appearing in this distance list. So alpha capital N is important. So how do we use this in practice? We can have a data graph like this, and we're gonna pick a number N, which is here like 4, and we're gonna randomly select 4 cliques from this graph. So here are random 4 cliques here. And because we have similarity scores, then I have distance lists. And because I have distance lists, I can compute alpha capital N, which is here 4. So here is 3, here is 4, here's 2. And as I'm randomly generating these graphs, then I get random points like this. Then I can basically compute PMF of these random points, which is alpha N basically. So I get to define a random variable on a data graph just by similarity scores. So this is going to be second to my last slide. So this is a simple experiment to showcase these alpha n's do carry geometrical information about the similarities. So here's the test. What we're going to do is we're going to generate a huge weighted tree like this, and we're going to subsample it, as I just mentioned, and we get cliques like this, and we compute alpha n, and it's PMF. So the PMF of alpha n is this black line here, right? And then I'm gonna propose a hypothesis test. I'm gonna say, okay, so this is the PMF of alpha n for a weighted tree. Should it resemble to random point sets in spherical, Euclidean, or hyperbolic point sets? So I randomly generate points in each one of these spaces, and I compute P of alpha n for each one of these spaces in like blue, green, and red. And I'm going to do some sort of hypothesis test. And almost in all cases, even with permutation noise and additive noise, the hypothesis test shows that the underlying geometry of a weighted tree should be hyperbolic space. And that's just from distance comparisons alone. We didn't use any metric information. We didn't embed the data points. So there's quite a bit of theory that goes along with this, but I'm gonna just stop. So in conclusion, we showed that metric and non-metric trees can be faithfully embedded in a hyperbolic space. We propose a semi-definite relaxation to solve HDGPs. And we showed that hyperbolic Procrustes is almost identical to its Euclidean version. We have centering, we have center masses, and translation and rotations. And also, finally, we showed that there is a good chance that non-metric measurements can encode geometrical information about their underlying point sets. And thank you all. If you have any question, I don't know, I didn't check if anybody had questions.
Thank you very much. No, you don't have questions in the chat, but we have some minutes to see if the audience will react. Any questions from the audience? Just speak in case of questions.
Hi, Antonio, I have one.
Yeah, please, Douglas.
Okay. Hi, Puoya, how I spell it? Puoya. Hi, Puoya. First of all, thanks for the very nice and interesting talk. I have a question concerning the applications and also this the third part of your talk, where you are discussing about the geometry of this similarity information, especially concerning the co-occurrences. For instance, in the natural language processing, it's a common problem to try to find word embeddings. And I think in this workshop last Friday, Sami Khalifi from École Polytechnique gave a talk showing how we could use Euclidean geometry to try to find word embeddings. And I'd like to ask you if you are aware of any work using hyperbolic distance geometry to find these word embeddings, and what could be the advantages?
Yes. Okay. So there is these two works that I cited here, and they both use hyperbolic embedding for words. Basically, Gramian especially, he proposed sort of machinery called like nested cones entailment to embed kind of hierarchical data, and you measured kind of pairwise hierarchy between nodes, and this is available in some word data sets like WordNet. There are some semantic hierarchies that comes along with this database, and what embedding aims to do is to respect these hierarchical relationship between these points. And and then they would argue that this would give a better or more faithful representation if you use the same number of dimensions. Actually, I'm not quite sure if they compare it with Euclidean, but the arguments is quite similar to what I just said, like that trees can be faithfully represented in hyperbolic rather than Euclidean. It can be they can be represented in Euclidean. They just need exceedingly more embedding dimensions, basically. So that's a trade-off. I don't know.
Yes, okay, thank you. And concerning the co-occurrences, what do you think? I don't know if you already performed some experiments or not. What do you think is the correct geometry to try to model the co-occurrences? For instance, if you take the, I don't know, the entire Wikipedia, okay, and you count the co-occurrences of words occurring in a window of a certain size. Okay, so this co-occurrence information or similarity could be more, how can I say, better represented by which kind of geometry?
I'm not quite sure about co-occurrences specifically, but we use some other metric to define similarities. It's called relative forest accessibility. It is another notion of similarities. And what we got for our data set, which was like single set RNA sequencing data, it was a spherical. We found the spherical to be the optimal embedding mesh. Actually, I have some results, but I didn't put it in this slide. So I think you just have to run this analysis, like this ordinal spread stuff, to give you a hint a little bit that like you would get a curve basically if you implement the algorithm that basically will lie somewhere between this blue, green, and hyperbolic. And then that would kind of give you an intuition which space it can be best that be embedded in.
Okay, thank you for the hint.
Any other questions? We have time for another question.
Antonio.
Yes.
Hello. Hello, Puoya.
Hi.
For this hyperbolic stuff, have you ever thought about using some Clifford algebra to code things or to deal with things like that?
Sorry, to deal with what?
To deal with this hyperbolic stuff, to use Clifford algebras to deal with this, to even mathematically or computationally.
I'm not sure. I'm not familiar with Clifford algebra, so I don't know how to answer that question.
Okay, no, it's just because Clifford algebra provides a good framework to perform isometries and
Oh, yeah, I see. What we were kind of looking after was basically solving this problem even for noisy point sets, like when there is no real isometry between them, and you want to find the one that minimizes some sort of error. But even this analysis gives you a little bit suboptimal solution. So no, I'm no. The answer is